Example 2, Site Selection Modeling. A company is looking for a new place to locate a resort in a mountainous region, shown here by this digital elevation model. And they want you to find areas that would be suitable based on avoiding landslide activity in the region. So you do research, either primary research or secondary research in the learned literature, and you find out generally that 90% of landslides occur on slopes steeper than 15 degrees. So that means that slopes greater than 15 degrees will have 90% of the landslides occurring there, usually, whereas slopes less than 15 degrees are unlikely to have much landslide activity. It's not completely zero, but it's less, so it's a more safer region. So based on that general knowledge, which is just made up here by just for your information, this is not real, we combine that general scientific knowledge with specific data, which is a DEM that we see here in a specific region. So we're putting together general knowledge with a specific geographic region. So we're combining generalizations with specific areas using the geography of a specific area. So in order to solve our issue or our problem here, we have to convert elevation into slope. So once we have a slope model, like you see here, from the elevation, then we can find out which cells have values less than 15 degrees. From a cartographic modeling perspective, that would require two processes being linked together. Elevation into a surface function called slope, and the output would be slope, some raster representing slope. Then that would be input to a relational operator, a less than 15 degrees. And the output would then show regions which are either suitable or unsuitable for locating this new resort, based on just this example of slope and landslides. So before undertaking anything, remember to you need to set your environments. And since we're using a digital elevation model as our single input, we'll set all our environments to that single model. So we'll set the output coordinate system to elevation, the extent to elevation, the cell size, mask, and snap raster all to elevation. So that's our control raster. So any outputs or intermediate outputs that we need to compute to get to our result will all match up exactly with elevation. If we are using the Python window for the first time, for example, or for a new map that's in a different area, we undertake our imports. Then we can do this, arcpy.resetEnvironments. This is a key phrase in ArcPy and in Python. What it does is remove any Python-specific environment settings. So it gets rid of Python-specific environment settings. That way, if you had set any environments in the Python window to some other layer on a different map, they'll now be reset to whatever you just set them in the global environmental settings. So you can inherit directly from there in the Python window. Or you can get your elevation raster stored in a raster variable using the raster function and set all of those critical environment settings in the Python window again. But in the case that we're doing, because we're making a cartographic model first and then going into Python, we don't really need to do this part. We should do a reset of environments just in case. And if it's our first session and we haven't closed and reopened ArcMap, we also have to do our imports. So we'll let the environment be inherited from the application settings for our Python session for this example. So here's the side-by-side comparison of a cartographic model and the Python program or script. In Model Builder, we have to have elevation going into the slope function to output a slope raster. Then we need a less than, and this should say 15 degrees, a less than 15 degrees. So a less than function from the spatial analyst math tools, logical functions, and we say slope less than 15 degrees, and wherever a cell is less than 15, the output will be 1. If it's greater than or equal to 15, the output will be 0. So 1 indicates that the statement here is true, that a cell is less than 15 degrees. 0 means that it's the opposite. A cell was not 15 degrees or less. In Python, we can create a raster variable called elevation from our elevation layer using the raster function. And we can have 15 stored in a constant variable called degrees. And the reason we do this is we set that degrees to 15 because later on we might want to change 15 to 25 to see what the effect would be. We can do what are called what-if scenarios. So what-if scenarios, easily by simply changing the degrees here to see how much area or what areas would either become available or be lost at different degree settings in terms of slope and degrees. So we have these two variables. Then we use the slope function with our elevation raster variable, and we output something called slope. And this is okay to have in Python because in Python, small s right here and a big S right here mean two different things altogether, because Python is a case-sensitive language. So we now have slope as a raster variable, and we have degrees up here representing 15 as a constant variable. So our suitable region will then be equal to slope less than degrees, which is 15 in this case. And that will produce the same result as the cartographic model. So we'll just erase this and summarize. So in summary, in cartographic modeling or in map algebra, we can take the elevation, create slope, find areas greater than or equal to 15 degrees or less than 15 degrees, depending on how you want to look at it, and have a result at the end. So potential locations here in dark green that do not exceed 15 degree slopes. So let's have a look at this in ArcGIS Pro as an example. Here in ArcGIS Pro, I'm going to go to my lecture, or I should say module 3 data folder, the same one we've used previously, and bring in the elevation layer into a new map. So here's our elevation layer. Now, one thing we have to remember is that this elevation layer has the cell values in feet, not meters. And we need to convert the elevation layer from feet to meters. Why do I know that? Because I've produced or I've given the data to you, and where I got the data from, I found out that the elevation was in feet. Now, this doesn't mean, that's important, in that whenever you get a DEM, you must look at the information called the metadata that comes with the DEM or elevation model and find out what the vertical units are. Are they feet or are they meters? Most of the time they'll be meters, but not always. So you have to know when you need to convert or not. Just because we're converting everything from feet to meters every time for this example, it doesn't mean that every DEM needs to be converted from feet to meters, because most DEMs are not in feet. So that being said, I want to set my environments. So analysis, environments. And so output coordinate system, same as elevation. Extent, same as elevation in ArcGIS. And then we have cell size, same as layer elevation, preserve resolution, and then mask elevation, and snap raster elevation. Notice I clicked on them anyway, even though they said elevation, because they may have been set for a different layer called elevation. So we got to make sure they're to this elevation layer, and I click OK. I'm going to go to my toolbox that I created for the previous examples in this module, and I'll right click and I'll make a new model. So that'll open up a model window right here. And I'll drag in elevation, because I know I'll need elevation. I'll make it a bit bigger. There we go. Just put it to the side. So the first thing I can do before I can get slope from elevation is the conversion of this elevation model to meters. So I'll click on my geoprocessing tab, and I'll go to the spatial analyst tools, math, and I'll find times. And I'll bring in the times, put it up beside it, like so. Then I'll connect elevation to times as the input raster or constant value 1. Then I'll double click on times, because you can see it's in a not ready to run state yet. We need to specify what to multiply elevation by. That could be another raster layer or a constant raster where every value will be 0.3048. And what happens here in the background is that ArcGIS Pro creates a raster that's the same size as elevation, where every cell in that raster has a value of 0.3048, and then it multiplies on a per cell basis. So for this second input here, the input raster or constant value 2, it's a constant value, and I'm going to rename it to that value so that I can read my model later on with ease. So I'll say 0.3048, like so. The output will then be elevation in meters. So I'll rename the output to elevation space M. It's actually better to do underscore M like that in a space, so we'll do that. So the elevation M is the layer that is going to be input to slope. So I go back to my spatial analyst tools, surface toolbox, subtoolbox, and I'll find slope right there. Whoops, I want to go back. There's slope. So I drag in slope. And I connect my elevation M to slope as the input raster. The output raster then is a slope. So I'm going to rename that to out slope or slope out. Like so. No, that's not what I wanted to do. Click, rename, slope out. There we go. So we have then elevation in meters going into slope, and then slope out represents a raster with every cell having slope. Now elevation M and slope in this model are intermediate things. So I'm not going to see them unless I right click on them and say add to display. But I don't need to see them. All I care about right now is the output, which is a suitability layer. And that will be based on comparing each cell in the slope out to the value 15 degrees, where cells that are less than 15 degrees will be given a 1 in the output raster, and cells greater than or equal to 15 degrees will be given a value of 0. So I need a less than operator now, or function. So I go to Math, Spatial Analyst, Math, Logical, and less than, and I drag less than in here, like so. Then I'll connect slope out to less than or equal to as input constant value raster 1. Double click on less than equals to enter 15 as the constant raster or constant value 2 that each cell in slope out will be compared to. And then I'm going to rename the input raster constant value 2 to 15. Like so. So I know that slope out is now being compared to the value 15 here. And then the output of this last process will be suitable, or the suitability layer. So I'll rename it to suitable. Like so. I'll do a auto layout, fit to window, and then a validate to make sure I'm not missing any parameters. So it's now in a ready to run state. There's color everywhere. Validation worked. Now I can run this model. So I'll click run, and we'll see in red each of the functions sequentially being run. And voila. Here we have now drop shadows. And that tells us that this model is in a already run state. So it's been run. And then I'll right click on suitable and just add to display. I could have done that earlier as well, but I didn't. And that will add it to the display. Now I'll save my model, save, and click back on my map window to see the suitable regions. So in this case, everything with a 1 is less than 15 degrees. And that's that bright green color. I think I'll make it, I'll just right click on there and make that yellow maybe. And I'll make black for the 0. Makes it a little bit more contrasty and easy to see. So all the black regions on here, or areas, are slopes greater than or equal to 15 degrees. All the yellow is less than 15 degrees. So the yellow areas then are the potentially suitable regions for locating this new building or resort. We can do the same thing in the Python window. So clicking back on the Analysis tab, and then Python. So in the Python window, this is my first session of the day, so I'm going to say from arcpy.sa import all. I'm not going to import my environment settings because they've already been set to the elevation raster. So all I need to do now is undertake my analysis in map algebra. And for convenience, I'll make an elevation raster variable called elev. I'll say elev equals raster, raster, and I'll choose elevation, like so. Next, I'll create a variable to hold the value 15 degrees. So I'll call it degrees equals 15, like so. Now, and I'll do in one statement the entire analysis that we just did. I'll call the output suitable to, just so we don't overwrite suitable. So suitable to equals slope LF times 0.3048 to convert it to from feet to meters, and then outside the parentheses less than 15. I'll put some spaces in there to make it more readable, like so. The spaces aren't necessary, just so you can read it easier. And then I'll hit enter. And now, if I look over, just move my Python window over, there I have my suitable 2 and my suitable 1. And these are identical. And again, to see if there are any differences between two map layers that are raster, that represent the same units, I can subtract them. So I'll say D equals raster suitable, raster suitable, that's from our cartographic model, minus suitable 2, which is a raster variable already. And everything should be 0 for D. And it is, in fact, all 0. In this case, it colored it blue. So every cell is 0, which means that suitable 2 and suitable are identical rasters, each created in different ways. One using a Python script or statements, set of statements, and the other a cartographic model.